So I have a charge here that is a distance L, and another charge here, a similar distance L away. And these are both positive charges. I was asking for the electric field at a point some distance away from the origin. We're going to call this the origin right here. And I think I said that this distance was Z. Okay? Now, in our answer, we can only have Q, Z, and fundamental constants. Does everybody understand? But our answer should have some interesting qualities. And here's where I want, before we start problems like this, for us to stop and consider what the properties of our answer should be. Because when we start diving into the math on this, it can get pretty hairy pretty quick. But ultimately, I find it important to understand the boundaries. For example, when Z gets to be much bigger than L, this should start to look like a big point charge of value 2Q. Wouldn't you agree? I mean, if I get really far away from this, see if I can do this. No, I can't. I can't zoom out. So I can't do it the way I wanted to, but if I get really far away, do you realize that these two are going to appear to get closer and closer together as Z gets bigger and bigger? So eventually, if I get far enough away, it's going to look like these two overlap. And I have a single charge that has value of 2 times Q. I would expect that the limit as Z gets much bigger than L should produce that result. At the same time, I should expect another limit. I should expect a limit where when Z goes to 0, the electric field also goes to 0. Which I think about it, when Z goes to 0, I'm looking at this point right here. What is the electric field at that point? Well, when I consider what it would mean for a point charge to exist there, a point charge would experience a force in both directions. So the electric field at that point should also be 0. Remember, the electric field is the force experienced by a charge divided by that value's charge. So if a charged particle experienced a force of 0, the electric field would also have to be 0. Are we following along with this argument so far? All right. Now, let me step back away from these arguments and talk about the method for doing a problem like this. Generally, when you're faced with a problem like this, you have to find the electric field, you have to look at one point charge at a time. Remember, the goal here is to utilize the concept of Coulomb's law. And Coulomb's law takes only 2 charges at a time. I'm interested in the spot here, so I put my test charge here. And I remind myself that the force between 2 charges is computed like this. The electric field at point P, which would be the electric field at the test charge, would be the force experienced at point P divided by the test charge value. Now, you do see that if I put these two things together, I get that the electric field at point P is just the value of the other charge divided by the separation distance to my point in space times k. That the test charge value cancels out in this calculation. this is a critical idea. And if you don't understand it, I'll need to review it a little bit more in depth. But for most of the year, we'll never use Coulomb's law again. We'll use the formulation of the electric field from a point charge instead. This is why I only talk about Coulomb's law for like a day or two, because we never use it again. If I ever need to find the force on a charged particle, I'll use the definition of the electric field to find that force. Are we okay with all this so far? Any problems yet? All right. So that's the physics of it so far. I'm going to get this out of the way for just a moment and rewrite it over here to the side that the force at point P, electric field at point P is Q over R squared K. Haven't spoken about direction yet. To speak about direction, this line I've just drawn represents R. That's the separation distance from the bottom charge to point P. Now, here's where it's going to get a little bit tough. The electric field here must be in that direction. I'll look about right. Angle's not perfect, but close enough. Now, that's the direction of the electric field. Now, normally I would say we should pay attention to that direction. But is that going to be the only contribution to the electric field at that point? No. Can you see that because this is a symmetrical example, we should consider the other contribution at the same time? And the other contribution, comes from this particle acting on point P as well. Since everything else is the same, this value for R is the same size as the other value for R. Everybody okay with that? Any question about that? However, it produces a contribution to the electric field that's in this direction. So I have two contributions to the electric field. Now, here's where we really have to bring every piece of your math together. Because when I'm talking about the electric field, I'm also having to talk about the vector side of the electric field. And do you see that clearly there are on-axis components to that electric field and off-axis components to that electric field, with this white line being this z-axis. And if you're not seeing what I'm trying to say, because there's a lot going on here, if I pick just this electric field for a moment, there's a contribution to the electric field in the z direction and an off-axis contribution to the electric field downwards. Is it clear to you that the off-axis components will cancel out? That for the down component, there's also an upward component. And based on the symmetry, those two components are equal. Is everybody okay with that? If not, speak now, because it gets just hairier from here. All right. There are two horizontal components, two of them. So if I find one, if I just double it, that's got to be the size of the electric field in the z direction. So I'm talking about finding the size of one of those red arrows and then just multiplying it by 2. Is that okay? I've already done that, by the way. This is the size of that value. If I find out how much to scale it based on trig. Let me, for just a moment, change screens so I can kind of zoom in here. Is that okay? So, page, and we are looking at each charge and how it contributed to the electric field. Step 2, identify the direction of the electric field. And how does it affect your answer? For us, we were looking at symmetry. There was symmetry in the answer. Step 3, apply Coulomb's law. That's what we did to get an expression for the electric field. Step 4, apply trig if necessary. And last, get everything in terms of your original values. We've done all of the really hard part, I think. We've applied all the physics. At this moment, we are trying to get the math part down, and the math part is not small, it's daunting, but that's all we're trying to do. Right now, we have, as an electric field, the total electric field at point P, 2q over r squared k cosine theta. That's the electric field. Our job now is to find a way to express theta in terms of L and Z, and R in terms of L and Z. R is going to be easy because I see a big triangle right here. Do you see a big triangle right there? And it's a right triangle. So I'm thinking Pythagoras tells me that R is the square root of L squared plus Z squared. Right, just Pythagorean theorem. And I'll point out that R is squared. So I can do that substitution. Not so bad. Any question about that? The next one's harder, but not too hard. Do you guys notice that this angle, which we called theta on the prior page, is the same as this angle, theta, here? Because they are vertical angles. Remember that? Freshman year geometry or 8th grade year geometry. Most people don't remember that far back, but you might. Vertical angles they're identical, which means cosine theta will be adjacent over hypotenuse. Adjacent is Z, hypotenuse is R. Or better yet, will be adjacent over hypotenuse. How are we doing so far? Eyes glazing over yet? You still hanging in there? Because if we can bring all of these pieces together, we'll be done. All these pieces together. So I'm going to start a new. This is the same question you've just done. Arguably the same question you've just done. There is a wrinkle here in that one of the charges is negative and one is positive. This problem has exploitable symmetry. You'll need to figure out what that exploitable symmetry is. This problem has a similar answer to the one you've just done. This is a dipole. That's what this is called. It's a dipole question. Dipoles are incredibly important in science. Those of you at AP Chemistry probably had discussions about dipoles. In physics, the reason why dipoles are important is because you can grab onto a dipole and push it around. You can twist it. You can turn it without necessarily repelling it or attracting it. That's how microwaves work. They use the dipole moment of water to cause it to rotate. So we will talk quite a bit about dipoles and their importance. This is your first dipole example. I would like you to run the numbers on finding me the electric field at this point. I want you to follow the same procedure as before. Work at your table, come to a solution. I'm gonna probably identify a few of you to help us put this together. But start by going through that set of steps and maybe consider what happens when Z is very big compared to L. And maybe consider what happens when Z goes to 0. Luckily, I can keep all this in my memory. I know that R is the square root of L squared plus Z squared. Cosine theta is Z over the square root of L squared plus Z squared. And my electric field is 2Q over R squared K times the cosine of theta. So we're going to bring these elements and apply them here. When we're done, we have an answer. So let's start. 2Q over L squared plus Z squared. When I square it, I remove the radical. Is that okay? Times K times the cosine of theta, which is Z over the square root of L squared plus Z squared. Now, this is the answer. It's not very pretty, but that's the answer. Let's combine some like terms. It'll be better if we do. So I'm going to combine like terms. We only have one like term to combine. L squared plus Z squared and the square root of L squared plus Z squared. When you multiply all that together, you'll get a single term that is L squared plus Z squared to the 3/2 power. Okay. Wow. I don't know about you guys, but that's rough, isn't it? It's rough. Now, we've spent almost 25 minutes getting to this point. I know this is one of the hardest things you've probably ever had to sit and follow, and maybe in your educational experience. But we had a test that we can run now to see if our answer makes sense. We said that if if Z was much bigger than L, it should just look like one charge that's value 2Q. Let's run that idea. If Z is much bigger than L, that's a big if, but if Z is much bigger than L, then this whole denominator really just looks like Z squared. Because it's so much bigger than L, L isn't really doing anything, right? It's like adding 1 to 1,000. It's still really just 1,000. So now when I look at this, Z squared to the 3/2 power is Z cubed. I have a Z on top and a Z on the bottom. That's going to cancel out one of those exponents, isn't it? Which, when I look at it in the finale, it's just Z squared. When Z's really big, I get a point charge of value 2Q. And the electric field looks like the point charge. That was our first test. Our equation passes that first test. Now, of course, we had another test, didn't we? What was the other test? Yeah?
If it's at the origin, it should equal 0.
So, if Z goes to 0, does the electric field go to 0? Looking closely, if Z goes to 0, it's right there. If Z is 0, the whole thing is 0. Not bad? Who's got a graphing calculator? Because you're not going to believe this, but on the AP exam, there are 3 follow-up questions to this if you can get this far. Now, the first follow-up question is to find the electric potential from this. Electric potential is actually an easier calculation, which we'll be doing in about a month. One of the other calculations is to sketch a graph of what this looks like. It might not be obvious to you, but if you get farther away from a particle, the electric field should diminish, correct? But this also diminishes as we get closer to 0, suggesting that somewhere out there in the middle, there's a part where the electric field is at its peak, maximum electric field. What does this look like if you were to sketch a graph of it? Now, if you have really good mathematical chops, you could probably envision what this graph must look like if you have good mathematical chops. If you don't, you might need a little help. Now, I only want first quadrant answer. What we're kind of trying to get is something like that. Now, your calculator can help you out with this. But to make your calculator help you out, you have to put this equation into your calculator. The easiest way to put this equation into your calculator is to make any constant other than z the number 1. And to use x for z. Meaning, if you're going to graph this, put in x over 1 plus x squared to the 3/2 and graph it. If you don't know how to do that, I'm not training you on your calculator today. When you graph it and hit zoom standard, you'll get all 4 quadrants, but you usually look at 1 quadrant. Yeah?
So why do you change the variables like that?
Because you can't put an L in there.
Yeah.
And we don't know what L actually means. What we want is a sketch, which is just the shape of the graph. So we clear out anything that could be in the way. The only variable that actually is fluctuating is our distance away from the center. So it's the only variable that needs to be plotted. Everything else can just be a simple constant. Now, if you're actually asked to calculate the maximum electric field, you wouldn't do it this way. But that's calculus anyways. Got it yet? Come on, y'all. Don't wait too long. You're going to get 1 in a 3rd quadrant that looks the same as well, because that's what this function looks like, but we only care about the first quadrant answer. But you should get something that looks like this. There'll be a clear peak somewhere in it. So, let me hit the pause button there. I know it's a lot to take in, especially first period. I mean, geez, who thought this class should be first period? I don't know. But if I'm zooming in and making this point P, all right, then there was, this electric field contribution out like that. That was Q over R squared K. That's the length of that vector. And we'll have a horizontal component. Ooh, that's messy. A horizontal component. And a vertical component. Now, that's a lot to take in, but this is a right triangle. If I just call this angle theta, the red component, the component in the z direction, would have to be q over r squared k times the cosine of theta. Is everybody okay with that so far? Am I hurting anybody's feelings yet? How many of those components are there? There are two. So the total electric field will be all of this times 2. That is going to be the electric field at point P from both charges. Now, I'd love to say we're done, except at the very beginning I said we could not have theta in our answer because it doesn't appear as one of the original variables. And we can't have r in our answer because it doesn't appear as one of our original variables. We can only have L, Z, Q, and fundamental constants, in this case K. I can have cosine in there, that's fine, that's an operation. Cosine can be there, but I can't have cosine with theta in it. I have to have cosine with L or Z or something like that in it. So I have to find a way of expressing theta in terms of L and Z. And I have to find a way of expressing R in terms of L and Z. So let's talk grand scheme of things for just a minute. Step 1, identify the contributions to the electric field. That's when we were on